In this lecture, I'm going to talk about a method of integration called partial fraction decomposition, which sounds very technical and very difficult, but it's not really. Although I will say, it probably puts two of your favorite things together, fractions and integration. But it's not that difficult, or at least it's not as difficult as the name might lead you to believe. So let me begin with talking about when we might use this. So start off with this example problem. If we wanted to find the integral, the indefinite integral, or the antiderivative, however you want to think of it, of x squared minus 6x plus 8 with respect to x. All right. Let me first, kind of by way of contrast, explain maybe how we've looked at things like this in the past. So if we had something like x minus 3 over x squared minus 6x plus 8, then we could use substitution here, right? So for example, we could let u equal x squared minus 6x plus 8. All right, so du would be 2x minus 6 dx, right? And then if we take both sides and divide it by 2, we would get that 1/2 du equals x minus 3 dx. And then we could just integrate 1 over u, bring the 1/2 out front, and here we go, right? Because the du covers the x minus 3 dx with the 1/2, and then u is just whatever our denominator is. So that's how we've covered things like that in the past. So just to kind of explain why that won't, so we can kind of see how we've handled things like this in the past, maybe help us understand why that won't work here, right? Because when I take du, I get this 2x minus 6, and I have nothing here that could be du. So some other method is going to be needed here. So one thing to notice in terms of this idea of partial fraction decomposition, the first thing to notice might be that this can be factored, all right? So if we factor it, what's it going to look like? We need two things that add up to -6, and when multiplied give me positive 8, so maybe that'll work, right? Okay. Right, we can follow that out to check, but that's how that's going to factor. And how does that help us? Well, what we'd like to do here is to rewrite this fraction, is the way you can think of it. We want to rewrite, so this is kind of a fraction where this represents one number and this represents another number that are multiplied. What we'd like to do with this integrand is to be able to write it as some number over x minus 2 plus some other number over x minus 4. If we can that might be easier to integrate. Why? Well, I can rewrite that. The a, if it's just a number, right? That's what we're looking for. The a can come out front, and I have this 1 over x minus 2 dx plus b, integral of 1 over x minus 4 dx. And how do we handle something like this? All right. Well, in general, if we have the integral of 1 over x minus c, where c is just some number, right? So here we could use substitution, right? U equals x minus c, so du is just dx, right? The c is a number, so it goes to 0, and the derivative of x is 1, so du is dx. And then we would just end up with integral of 1 over u du, and then that would give us natural log of the absolute value of u plus c, or the natural log of absolute value of x. Well, okay, maybe use a different let's call that d. Then we'd have something like this, just to differentiate that this c and that constant that's added on here are not the same thing. Anyways, the point here is that if we can get something into this form, we know how to find the antiderivative of that. It's just going to be natural log of whatever's of the absolute value of whatever is in the denominator. So that's why being able to break it apart like this would be useful. So what I would like to do is, we'll come back to this. I want to kind of just go on a bit of a tangent here. Not really a tangent, but kind of an analogy in terms of how this would work. So let's look at something, we'll bring that back, but let's look at something like 5/12. All right, just a fraction, because this is also just a fraction, right? So if we can kind of use some reasoning from what we could do here, then we could apply it to something more complicated. So let's say we can rewrite that as 5/3 times 4. And we're wondering, another way to think of this is, if I wanted to rewrite this as something over 3 plus something over 4, right? Because I would get a common denominator here between 3 and 4. Well, that would end up being their product, right? That's the least common multiple between 3 and 4 is their product. And so if we think about what those numbers would be, such that when I add this together I get 5/12, that's kind of the same idea here, right? So notice we have 5/12, we want it to equal this. So one thing we can do here is, let's multiply both sides by 12. So that just gives me that 5 equals, now if I distribute here, the a/3 times 12, well, the 3 goes into 12 4 times and just leaves me with 4a, right? And likewise, when I distribute the 12 to the b/4, 4 goes into 12 3 times, and I'm left with 3b. So what I need is to kind of find a number, or find numbers a and b, that I could put in here where this would end up being 5. So, one way is to let's just pick something for a. So if we let a equal 1, then I end up with 5 equals 4 plus 3b, subtract 4 from both sides, so I have 1 equals 3b, so b equals 1/3. So coming back up here then, 1/4, right? Sorry, not 1/4, 1/3, right? Because a is 1, so if I put in a 1 for a, I get 1/3 plus, and b is 1/3, so it's 1/3 over 4. Well, that's just basically saying 1/3 divided by 4, or 1/3 times 1/4. So this is the same as 1/3 plus 1/12. All right. Now let's just check to make sure that works. Well, 1/3 in terms of twelfths, that's 4/12, right? Plus 1/12 equals 5/12. All right. So that works. You just found something that, so if we take these two, then we get something that actually does give us 5/12. Now, we didn't have to choose a to be 1. We could have let it be any number and solve for b. The other thing is we could have let b equal 1 and then found a value for a. In this case, there's an infinite number of possibilities, but this is generally how it works, is that we want to try to, first we do what we call clearing the denominator, right? We got rid of the denominators here, and we ended up with something like this. We just, by multiplying by the denominator of this. We're going to do something similar here, and that's why I wanted to go through that example in terms of fractions, which you're a little more familiar with, even if you're not any more endeared to than things like these rational functions. So what I want to do now is think about what could I find, how I need a and b. Well, ultimately what I need is I need this integrand right here to be the same as this integrand. I want them to be equivalent, right? Because this equals this, and now I want a and b so that they're all equal, because ultimately this is what I'm trying to find the antiderivative of. So what we can do is set them equal, right? So we've got 1 over x minus 2 times x minus 4 equals a over x minus 2 plus b over x minus 4. So just like I did in this example where I cleared the denominator, I want to clear the denominator here. So I would multiply this by x minus 2 times x minus 4, and then over here I would do the same thing, multiply by x minus 2 times x minus 4. So here this cancels with this, and I'm just left with a 1. And just as we saw here, right, when we multiplied this, 3 went into 12 4 times, 4 went into 12, 3 times. We're going to see some cancellation here, right? This x minus 2 cancels with this x minus 2, and I just left with a times x minus 4, and then multiplying here, this x minus 4 cancels with this x minus 4, and I'm just left with b times x minus 2. Remember, I've got to take this, and I have to distribute here, and that's where the x minus 2's cancel, and then I also have to distribute it here, and that's where the x minus 4's cancel, leaving me with b times x minus 2. Now at this point, there's a number of ways to proceed, but I think the easiest is to try to basically cancel out one of these by choosing an appropriate value of x. So for example, if I want to solve for a, then I want to eliminate b, and I want to choose an x that would eliminate b. Well, clearly if I let x equal 2, then b is gone, right? So if I let x equals 2, then I have 1 equals a, 2 minus 4 plus b, and 2 minus 2 is just 0. So I'm left with 1 equals, and that's going to be negative 2 times a, so a equals negative 1/2. Alright, now likewise, if I want to solve for b, then I eliminate a, and here clearly x equals 4 would do it. So now I'm going to take the same equation and substitute x equals 4. So I end up with 1 equals a times 0 plus b times 4 minus 2. That leaves me with 1 equals 2b, or b equals 1/2. All right, so I know what a and b are. I'm going to plug in here. So coming from this, I have now that I have negative 1/2 over x minus 2 plus 1/2 over x minus 4. I want to find that integral. All right. What do we see? A, negative 1/2, b, 1/2. Plug it in. Now, I think we could simplify here, right? We could make this negative 1 over and then distribute the 2 across here. But because of the property of integration, whoops, sorry, off the screen there, we can just bring these out front, and that's a whole lot easier, I think. So we're going to use the fact that the integral of a sum is the sum of the integrals, and also the fact that this constant can be brought out front. So we can now rewrite it negative 1/2, 1 over x minus 2 dx, that's our first integral, plus, bring the 1/2 out front, integral of 1 over x minus 4 dx. And now we can come back to this property that we've already established, that 1 over x minus any number just will give us natural log of the absolute value of x minus c plus some constant. All right, so this gives me negative 1/2 natural log absolute value of x minus, whoops, I'm not working with the c anymore, it's 2. And that's going to have a constant added to it, but if we call this c1 and this c2, then together we can just call them c. So I'll just add my constant of integration at the end. Now, plus 1/2 natural log absolute value of x minus 4, and then add my plus c. Okay, so you could then differentiate and make sure, you'd have to do some simplifying in order to get back what we started with, but it would work. We also could simplify this a little bit further using properties of logarithms, but, well, let's go ahead and do it, because then if you want to check your answers in the back of the book, you can maybe make sense out of them. So the first thing we can see here is I can factor out a 1/2. So I've got this 1/2, and I'm going to rewrite this to the negatives in the back. So I'm going to have natural log of absolute value of x minus 4 minus natural log of absolute value of x minus 2 plus c. And if you recall, properties of logarithms, the logarithm, or the difference of logarithms, is a logarithm of the quotient. So this could be rewritten as 1/2 of natural log x minus 4 over x minus 2 plus c. We could actually go a bit further and bring this 1/2 up here, so we're taking the square root. Anyways, just a reminder about some of these properties of natural logs, because this might be along the lines of what you'd see in the back of your book. All right, so that's basically partial fraction decomposition. You take something like this, we break it into linear factors as opposed to quadratic, just an x plus or minus something. Then we separate and solve for those numbers, whatever A and B are, by clearing the denominators. I'm going to do one more video after this, a little bit more involved example, but this is just an introduction.